Start recording. Okay, so today we're gonna talk 6.5, 6.6, and 6.7. We're gonna start by talking about something very natural after you have state, which is you can now have stateful collections on top of it, and there is a very cool and nice diagram depicting the relationship between the stateless things and the stateful things.
This is a really nice diagram, actually.
Yeah. So in summary, which I think we can summarize all these 6.5 altogether. Before we had stateless data structures, which were tuples and records. So with tuples, you can retrieve information by using the integers as indices, and by records you can use any more literals than that, such as atoms, for example. But if you want to change their content, you have to create a new one, a copy of the old one, changing whatever you want, so they are stateless. If you grab the tuple, and if you are fine with using integers, just integers, and you add state to it, you have arrays. And if you have records and you add states to them, you have dictionaries. And if you from arrays, you also want the flexibility of using atoms, for example, you can just go from arrays to dictionaries as well.
This gives me category theory vibes looking at this diagram.
Category theory vibes. Okay, then we have an API description on the operations that you can do in arrays. Nothing too crazy. Same thing for dictionaries. Um, there is a caveat on the dictionaries that they have amortized constant time because sometimes you have to do some machinery things
Ah,
inside for
right.
additional
You may have,
removal.
yeah, you may have to resize it occasionally, and that's not constant, but as we saw, you can
Yeah,
space out that operation
so it's amortized
by,
constant time.
yeah, by choosing the new chais carefully. You can make it happen
Less often.
less often enough that, uh, like, if you spread out the cost over the addition or removal operations, it turns out to be constant, which is, yeah.
Yeah. Yeah, and then you have again an API on dictionaries. There is a very nice trick that you can convert stateful data structures to stateless by transforming them to records. Uh, and then, okay, this is basically the TLDR of which one to pick. Tuples are the simplest ones. They are the more efficient ones. But the first they're stateless, and you can only use integers for indexing. Records they are the second most efficient ones, but they can use more literals for indexing. Um, yeah, I think that's pretty much it. And arrays, they are more flexible than tuples because the content of each field can be changed, so they're stateful. Accessing an array field is extremely efficient because the fields are stored consecutively. The fields are consecutive integers from any lower bound to any upper bound. Yeah, this is actually pretty interesting. I should mention this. We should not skip this. Arrays in OS, they actually allow you to not start from zero, which is weird.
Actually, you would start from one because it's one based, but yeah, you can start from any number.
Yeah. I think that there's a hack using lexicoscoping. In the internal machinery, they actually do start from zero, from one or zero or whatever. But when you are doing the using the API, the lexicoscoping allows them to just add up the L that you
Um,
provided when initializing the array.
yeah, I'm guessing the array stores an offset, so it can
Yeah,
internally store them like from zero, but then you apply the offset to the index, and that lets you have an index that
yeah,
doesn't actually map to the physical structure, right?
exactly. Which is a very nice trick, right? This is the power of lexicoscoping in a language that allows you to go to this extent of having a mutable thing under the lexicoscoping thing. Cool. Yeah, so there, and then we have dictionaries, which are the most general. They are the more expensive ones as well. They are amortized constant time because of what we already described. You can use any literal to index them. Order collection, unindexed collections. We have seen two of those, lists and streams. Right, so streams is the difference lists. So actually, these are just lists, but it has particular implementation for streams. What is interesting to say here? Lists are of finite fixed length. Streams are incomplete lists. We have the tail being unbound, of course. The stream is one of the most
Yep.
efficient extensible collections in both memory use and execution time. We have seen this before. This is the code for the next thing. And we used the streams for stream programming and message passing. Nothing new. And then you have extensible arrays, which well, they are inefficient because if you have to extend them, you have to do some copying. But you can extend them. So essentially, the summary of this code is you check if you're trying to use an index that is outside of the boundaries, and if it is, you do a clone of the array and you copy the contents of the original one.
Yeah, and you make a new one that's twice as big. It doesn't
Exactly.
have to be twice as big
Yeah,
exactly. It
this
needs
is
to
arbitrary, right?
can be any factor that you multiply that's greater than one should work.
But there are probably some
Java's array,
statistics about this.
yeah. For instance, Java actually has an array list collection, which is basically this, and they use a factor of 1.5 if I'm not mistaken.
Okay, I didn't know that. And then you can just extend them. Well, at least it's transparent from the caller's perspective. You don't know that you are actually. Well, if you do profiling, you're gonna notice that there is a performance hit into this, but when using it, you won't. And then 6.6, which is gonna piss a lot of people off because this is saying that yes, programming does involve math, and all of those guys on YouTube saying that you don't, they are wrong. So this is gonna piss a lot of people off.
And this is using horse formalism, no? Yeah, he mentions Hor by name and Dijkstra as
Yeah,
well.
yeah, but let's make something very clear. Um, Even though it's mathy in a way, what we are about to say here, you can actually like bend the rules and say that these are just property tests. People like to use that name, property tests.
You're
Uh,
also pretty much going to have to do this informally anyways. Like you can't really escape this.
no, no, no,
Even if you don't
no,
want
no,
to
but that's
do
the
to go
thing.
to the
That's the
yeah.
thing. It's a good thing that we can bend the rules and say that these are property tests because then people are less afraid of it. Because when you
Yeah,
say
that's
words like invariants and assertions, and there is a portion there is a paragraph that starts by saying that assertions are a mathematical concept. Where is it? Yeah. Uh, no, it's not. Yeah, this. There are some differences because assertions are mathematical expressions used for reasoning, not program fragments. So like the book tries to push you into a path of understanding that actually there is a known nullable intersection between programming and mathematics, but that scares the shit out of people. So what we can say is that even though the book treats it that way, if you are that scared, just treat these as property tests. Like you're gonna write something that resembles this in a programming language, and you're gonna call that a property test. So um, I think that's the way to do some marketing on top of this. What we're gonna be doing? We're gonna try to establish an approach to interact with state because the stateful model allows us to do more stuff, but it becomes more complicated, and there's an even and there is this is the explanation why programs that use state is a haphazard way in a haphazard way are very difficult to understand. For example, if the state is visible throughout the whole program, then it can be assigned anywhere. And this is the reason why global variables are usually considered are not a good practice.
Uh, Counterpoint. Isn't a database basically just a big giant global variable?
Yes, but databases they have the concept of transactions, which diminishes a little bit of the pain of having them globally accessible.
Well, if you have only one global variable and as reassigning it is atomic, then you can get pretty much most of the same
Yeah,
benefits.
but
Actually,
if
that's
you have
the
multiple global variables, such as a struct, and you don't have the concept of transactions,
actually you can have a struct inside of a single global variable. The problem is not the size of the data; it's whether or not the data under the variable is mutable or not, right?
not only that, if I have a struct, which is a single thing, but I distribute pointers of the fields inside the struct for
Well,
multiple
but
other
then
people,
but then if you do that, you would now effectively have multiple global mutable variables, right? The struct is mutable. You have a mutable thing inside of another mutable thing, and obviously if you take a pointer into the struct which is mutable, that's also mutable. So
yeah, and then the that's why it's this is the reason that's dangerous is because anybody in any thread in any maybe even outside of that process maybe a different program if they have access to it they can assign something to it and that may do a side effect somewhere else. It's the same thing as the data flow variables, right? That's why the book spends some time talking about persistent data structures because it acknowledges that the data flow variables are they have a hint of mutability already. Even though they were introduced in the declarative model, they do have that. They do have a side effect property that a separate thread gets notified when a data flow variable was assigned by somebody else. Um, and then well, let's continue. The only way to reason is to consider the whole program at once. So you have the entirety of the state machine, and because anybody can do any assign if they have a reference to it, that means that in order for you to reason about it, you have to consider a more holistic approach to it. And that is the reason that this makes programming on the big very hard, because as programs get larger and larger and larger, and you have different teams working on different portions of it, it starts to be non. How should I say it? It's very inconvenient and more error prone for people to try to have all of that information in their brain, especially because they will probably not write all of it. Because one of the things that I notice of people that are in favor of like stateful model for everything, not only is because it's easier to map to the machine, and then there's a whole philosophical debate about should programs be what we think or should they be what the computer can do. But there's also the problem that usually these people they work on the entirety of the project, so they do have the context, and usually they are very smart people, so they can actually hold all of that amount of information in their brain, and then they don't have this problem because they do know what the fuck is happening. They wrote out of it. They are very intimate with it, so they do remember everything about it. Such as us, for example. Even though we are very well-disciplined people, and we make, for example, the first version of Karuta in a whole immutable manner, if we did go mutable on that, probably you and I would be very comfortable with it because we wrote all of it.
I wouldn't be actually.
Well, I wouldn't be because I know I am like doing it wrong, but I would be comfortable in the sense that I know what the fuck is going on. It's a sequential program. There's no parallelism or concurrency. Even if the data structures are mutable, I would probably know what the fuck was going on, even though I would not necessarily suggest uh, in being in favor of using that approach. If we did, like you and I would be fine, and my Geta probably would be even more lost on it. You see? Um,
Um,
okay. Do you have anything to say before we continue here? I think this is the main thing for us to talk about today. Like this and the next one.
yeah, if you're gonna have state, it's better to just have a single piece of state and everything under it is immutable, and then you can do transactionals on top of that. Um,
Yeah.
if you have to have multiple pieces of state, be very careful.
Yeah. Um, so we're gonna try to add something on top of state to allows us to have an easier time thinking about it, which is gonna be invariant assertions. We show how to use the method for programs that have both stateful and declarative parts. The declarative part appears as logical expressions inside the assertions. We also explain the role of abstraction and how to take data flow execution into account. And then there is the credits, right? So these invariant assertions usually called axiomatic semantics, and this is the begin. This is more names, like more names. People are scared because people are afraid of names. So axiomatic semantics, these very important people used in the past were initially developed in the 60s and 70s. The correctness rules were called axioms, and the terminology has stuck ever since. And
Side note, for some reason, all of the coolest things in computer science are from the 60s, 70s, and 80s.
that's that that's what I keep saying. Like if you read um, Dealers of Lightning, if you read The Soul of a New Machine, if you read this book has references. Uh, that was a period we all the nerds should have been born between the 60s and the 80s. Like that's where the main group of ideas they were developed. That's where people were more like enthusiastic about it. That's why I think we were all living in the wrong period, man. Yeah. So more evidence that we were. This is the wrong time. Okay. So what the heck are invariant assertions? They are essentially property tests. So there is a particular notation that we should read, but I don't know where to start.
It's in the next page.
Yeah, so I think I will skip all of it. Well, not all of it, but I probably this paragraph. I'll read that. Each operation of the DDT is specified by giving two assertions, which I think this is already a bad start. Like this should be B and this should be F for before and after. Uh,
uh,
the specification states that if a I is true just before the operation, then when the operation completes, B will be true. So this is the syntactical
uh,
notation for this pseudo language that we're going to be using.
Also, there's another name you could. Yeah, this is mentioned in the text actually. If you are doing like design by contract, like Bertrand, Meyer, and all that, or if you're doing rackets or whatever, yeah, these are basically just pre and post conditions.
Yeah, pre and post conditions. The specification of the completed DT then consists of partial correcting assertions of each of its operations. So let's go through an example. So this is the example of a property test, an invariant assertion of the operation new stack. So the precondition is true. It's const true. Why? Because there's nothing for us to check. So this will always hold. And then we do the thing, and then we have to parse this very like it resembles Oz in a way, but there is also special symbols such as this that we have to go through what they mean. The precondition is true, which means that there is no special conditions. The notation at C denotes the content of the cell C. And the reason there is familiarity. We've already seen atoms before, or whatever they call it in here. I already forgot, but they're closure atoms. Uh,
Yeah, those are cells in
cells.
Oz parlance.
And then we are checking that the content of it is new. And why is this a pseudo language? Because the scoping here is kind of fucked, right? Like there are no like take if this taken literally would not make sense to you because where the heck C comes from. So that's why it's a pseudo language. This specification is incomplete. It is not defined whether references push, pop, and is empty mean. So let us define each of them separately. We start with push. Executing this is an operation that pushes X on the stack. So if you have, again, a C that comes from somewhere, and it starts by being S, after you execute the push, this is the predicate that we expect to be holding. which is essentially saying that you push X on top of as the first thing to S. The specifications of new stack and stack push both mention the internal cell C. This is reasonable when proving correctness of the stack, but is unreasonable when using the stack, since we want the internal representation to be hidden. Yeah, this is also like leaking the implementation of this stuff. So we can avoid that by having a black box called stack content with the following definition. So you are hiding this internal implementation by using like
By using a
obscure,
predicate in the by using
yeah,
a predicate in the meta language.
yeah, where C is the internal cell corresponding to stack. This hides animation of the internal cell from programs using the stack. So then you can rewrite the stuff. So if you do new stack, you can check that the stack content is new, and the stack is equal to a record that has these operations. And you can do the same for push. You're checking that the stack, after popping, the content is not new, right? And is equal to X. So this is actually a pretty interesting use case because, in my opinion, it could have. Oh, actually,
Actually, you're
this is
checking
missing
the.
parentheses.
What
This
do you
is
mean
what is.
missing
This
parentheses?
is the equality that we care, right? Not
Uh,
this is equal to
Actually, you
this.
care about both because you see, the precondition says if you have an X on the top of the stack, which must not be empty, then after you pop, the X will no longer be on top of the stack, but it will be bound to Y,
Exactly.
basically,
So
right?
there is parentheses here, and I just noticed that. Okay. And then here you're checking if the thing is empty, which is essentially saying that if you have a stack with contents X, and you check that it is empty, this should be true. So X
If S is
equals
new,
new
basically.
if S is new. Yeah, but why do you need that? That's kind of.
Well, because it could be false if S is not new, and that would be okay also.
Yeah, but I feel that this is also complicating the thing. Why can't you just put stack in the beginning? You put this S equals to new as a conjunction in here.
Because you don't know that before you call it is empty.
No, you do. You have control over the precondition as well.
No, no, no. The precondition is if you have a stack and there is
No, yes, I understand that you decided to go with a more general precondition and add a stronger post condition to it. I'm saying that I think it's more readable to do the opposite.
that doesn't make sense, Lemos, because this is the post condition of a predicate.
I don't understand.
It,
If you
if you
have
call
access to
up,
whatever predicate to be true before doing the operation,
no, 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 Lemos. If is empty is a predicate, it should give you some information, right? So logically, the post
sure,
condition should have more information than the precondition, right? Otherwise, the predicate is not really telling you anything.
that's not true. That's not true. Okay, so I would propose two tests, two invariant assertions. I think this one is less readable than what I'm proposing. I would have one in which S is 100% guaranteed by the precondition to be empty, and then I would just check that X is true. And I will have another one that the precondition guarantees that S is not empty, and S, the opposite of X, is equal to true. Easy as that. This way, it's combining the two things at once, so whatever S is, it's fine. And I understand that. I just think this is harder to read than having two.
Mm, the problem is that if you have two, then effectively you're putting an OR in the precondition, right?
Yes, I am. I am. I understand that that's true, but I personally I think that's more readable. I have to think way more about this one than I have about them having two of them. And maybe it's just me, but I think I like to keep these sort of tests as retarded as possible, like as simple as possible. That you you gonna take less than 5 seconds to understand. And maybe just me, but I think this takes me more than five to understand.
Okay,
Maybe
that's
just
fair.
me. The full specification of the stack consists of these four partial correctness assertions. These assertions do not say what happens if a stack operation raises an exception, which is true. Proving an ADT is correct. So then you go and you create your stack. We've seen this before, nothing too crazy. And then, okay, this is actually pretty cool because it's teaching you how do you convert the code of the language to the code of this meta language. So you have the push procedure that's going to be happening on the stack record now, and then if you want to prove the insertion invariant assertion, you have this precondition, which we can expand to this, right? Because we know the internal implementation in this case, so we know that this is equal to that, and then we just pay these can stay, and then we have the post condition, which is what should be verified after the operation. The stack ADT uses the cell ADT in its implementation. To continue the proof, we therefore need to know the specification of the cell operations. So then we go to the translation table that we have for OS that I already forgot where it is, but usually we have a bunch of tables that lists the kernel language primitives, and then you
Yep.
swap those in essentially, and then we rewrite this in terms of that. So you have a precondition that we call the P, a predicate. Then we swap this by this, which is a more generic form. Like it's getting tougher to read, but it's getting more generic. And then you test that the precondition is true as well as this assignment is being true, where y is an identifier, x is an identifier bound to a cell, and p is an assertion. The specification of column equals is this, which makes sense. Blah blah blah. And then let's apply the proof rules to the definition of push. We start with the assignment statement and work our way backwards. Given the post condition, we determine the precondition. In our case, the post condition is this, matching this with that. We see that x is the cell C, and p of reading the C is going to be equal to that. Blah 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 blah. This is a mechanical process of translation, so it's not crazy. And then we end up with you start with the content of C being equal to S. So then you save into a variable S the contents. Then you check for that. Then then we have to translate this, and it becomes like that. And this is the post condition of that. And it's getting messier because you have to include the semantics of the reading and the assignment. And then essentially you have to do that for everything. Uh, that we're going to get there. So now we have assertions. An assertion is a Boolean expression that is attached to a particular place in a program, which we call a program point. The Boolean expression is very similar to Boolean expressions in the computation model. Um,
Um,
Go on.
it's kind of interesting that it takes the time to say, yeah, um, those are not actually program fragments. That's something worth remembering.
You mean these, right?
Yeah, the assertions, the pre and post conditions.
Yeah. These are not like this is a pseudo language. Everything in the curly braces it's a pseudo thing. They may remind you of us, but they are not. They have a particular semantics. Uh, I think what matters for this is that we are introducing these guys.
Quantifiers.
Yeah. To evaluate an assertion has to be attached to a program point. Program points are characterized by the environment that exists there. Evaluating an assertion at a program point means evaluating using this environment. We assume that all data flow variables are sufficiently bound so that the evaluation gives true and false. This is a very strong assertion, like, premise for this.
Yeah, we eventually address that. Like it's closer to the end of the section, I think. Like there's a section that goes, okay, we assumed so far that everything is peachy and rosy. How do we check that it actually is, right?
Exactly. Using and then we introduce the operators for this as well, which well we were already using before. So yeah, I think that these two sections should have been reversed because like it starts using the operator here, but introduces it
That,
formally to us down here.
I think. Hmm. Oh yeah, that is true actually.
And which well for us it's fine. We've seen these operations before because we know logic, but for a new, well, I guess because the book is not targeting like newcomers as the target audience, it's fine. But I don't see the gain of swapping the natural logical of introducing those terms. So then we have the for all and there exists. Um, yeah, the reason techniques introduced here can be used in all stage pro languages. In many of these languages, well, there is a caveat to that because yes, this is true, but it's not in every language that you're gonna have an easy time doing these translations between the actual implementation of something and its pseudo meta version. Because some languages they don't even have a kernel language to start with. They have more ad hoc approaches such as C++. So I imagine that doing this sort of thing in a C++ type language, this would be like a page.
You would have to dive very deep in the language standard, which is massive, right?
Exactly. So you have to simplify some of it. I don't think you can go all the way to whatever kernel um, ish thing you have. For example, in the Java, are you going to go to the bytecode of the JVM? What are you going to be doing about that?
I mean, Java is actually pretty straightforward compared to C++ because like you
Okay,
don't have
everything
operator
is.
overload. Well, you don't have operator overloading to begin with, right? So that's one point in favor of Java, and I don't believe I'm saying that.
Yeah, that's very funny. Since there is no ambiguity, the at symbol can safely be left out of them. In our model, we keep at because we can distinguish between the name. Yeah, this is also very nice that we are keeping the both versions of C because we have a syntactical element to differentiate what they mean. Because that's actually something that the book should, in my opinion, should have spent more time on it. We have to define the semantics of the meta language. Here we're kind of being loosey goofy about it because it's fine, but in a more proper scenario, we need to have a specification of what the fuck happens inside the curly braces. Right now we're just going like out of like vibes and sure, and that's okay. But if we want to do this properly, we should have like a grammar, like all that stuff. But again, this is just like putting the tips of your toes inside those waters. This book does a lot of this actually. It just puts you into the direction of doing some math, but it doesn't
and
it
then it,
doesn't kick you on that direction.
and
If
then
that
it
makes
says,
sense.
yeah, and if you wanna actually go there, here are other books you can read, right?
Yeah, yeah. He basically says, "I'm not gonna kick your butt. They will. So you talk to them."
Yeah.
Uh, so that's usually how that goes. So let's continue here. So then we have binding. Again, a bunch of translations ish about how to make every single operation in the pseudo language. I don't think it's worth going through like all of them in detail. Well, but we do make some compositive ones because otherwise our lives would be terrible. So we make
Right.
conditions.
Right.
So these we are basically specifying what this means in this language, in this meta language, and then we start seeing that okay, we have to take in consideration the then branch and the else branch,
Can I
and
just can I
sure.
just say for a second that this is very evocative, probably deliberately, of sequence calculus. Like you
No,
see this all
even
the
even
time
even
in
lambda calculus in a way.
no, no, sequence calculus specifically, because you see this kind of the vertical bar with the premises on the top and the conclusion below. You see that all the time in papers about type systems and also
Yeah.
formal logic.
Well, the reason that I said Lambda calculus is because this is also written in here. Yeah.
Well, yes, but this is not lambda calculus. It's the sequent calculus being used to establish the rules for the type system of a particular lambda calculus,
That's
right?
fair. I didn't put all of that preface, and that's fair enough. That's on me. But yeah, you're right. So yeah, we have the horizontal bar for procedures, and then if they have external references for some of the arguments and all of that. Then we make the while loops. Again, this is just a construct to facilitate proofs that can utilize some like higher order concept of having a while. And then the same
I
applies to
like the
for
fact
loops.
that the book says that, yeah, proving this by hand for a loop every single time is kind of sucks. So let's prove it for loops in general, and then we can use the abstraction, right?
Yeah, but
Because
I don't know about you, but this sounds way more useful than this because the way that we implement for loops, these are particularly the for loops that use the integers for traversing it. This is way less useful. What if I don't have a for? Because OS supports for loops that are like for element in collection do something.
well,
For those,
well, you
this is not useful.
well you can desugar that into this if the collection is indexed by a number, right? At
No,
least.
no, but then it goes to the whole summing. Like this for loop abstraction for helping with proofs. This is particularly for the case where you're doing an accumulation of the things. The while can
Actually,
do anything,
actually,
any
actually,
expression.
actually, the accumulation is just what it gives as an example, right?
No, no, sure, but it's also you doing the while as example when the while seems way more useful because the while is not locking what the statement may be. This one
Well,
is.
well, it isn't actually. The statement is
Well, it is.
parameterized.
No, the
No, it
statement is
isn't.
parameterized. Oh, actually, you're right. Like, it's just a plus in this case. Well, if you want it, I have it.
No, no,
If
no,
you
no,
don't,
no. No, no, no. The statement, the actual statement,
is
is
this
on the previous expression actually.
previous expression. I don't
Yeah,
see it.
that I plus one is just stepping through the loop, right? That's incrementing the loop variable. The actual statement call is in the right after the then you have statement I. You see?
No, I think you're right. I think the accumulation is just a plus. Like when I say a plus, like a nice to have,
Yes.
because for example, if I'm doing the other four that I don't care about the number, you can desugar that to this one, and I just don't care about the integers, right?
Yeah, you wouldn't care about the well, you would have to put the fact that you were walking through a list into the body of the loop if you do the desugaring, right? Which is perhaps more complicated than you want, but it is what it is, I guess.
Yeah. No, but this is at least giving me the option that if I care about the accumulation, which I may care about it, right? Uh,
Right.
that's fair enough. But I take that back. I was wrong. This is just giving you as like if you want it, I have it, but the statement is being iterated as it goes, so I may do anything with it. And then there is the math to do the accumulation for you, blah blah blah. So reasoning at higher levels of abstractions. So these are observations. The while and for loops are examples of reasoning at high level abstraction in the kernel language. For each loop, we define the syntax in its translation to the kernel language and then gave a proof rule. The idea is to have a book defining all of those, so you can use it as often as we like. This approach, defining new constants and the proof of rules, is the way to go for practical reasoning about stateful programs. And this is the problem. This is actually the problem. Uh, this means that's going to be laborious. Like it's going to take some time. Somebody's going to have to be paid to do it, and that in the whole worse is better philosophy of the world, this is usually not appreciated because well, there are multiple reasons, but not only because people are afraid of math or mathy things, but it's also because this doesn't have an immediate value for people that don't understand the long term, because they may see it at okay, you guys are proving all of this, but how can we market that? Or is that going to be good marketing for our language? Do we rather spend that money on something else?
Yeah, yeah.
So no, usually that won't happen. For example, Karutov, right? Let's say in the future, 2026, we have all the examples that we had working, now working with the current version. So like we have list operations, we have built-ins for arithmetic. We have, and let's say even that we have the database thing working. Why not? Are we gonna do this? Because if the database works, then it is a stateful program now. Are we gonna do that?
That's a very good question, Lemos.
We should. We definitely should. But I don't know if we will. And we know that we should. That's actually the main thing. We should. We know it. Aliasing. The proof rules given above are correct if there is no aliasing. They need to be modified in obvious ways if aliasing can occur. For example, assume that C and D both reference the same cell and consider the assignment this. Say that the post condition is that, but we have an alias on D, right? The standard proof lets us calculate the precondition by replacing. This gives an incorrect result because it does not take into account that D is alias to C. So you need some sort of
Yeah, you need to keep
what's
track
the name
of
of this
when.
unification on the front end of the
No,
compiler?
it's not really unification. It's uh
Alias treatment or whatever. There is a name
yeah,
for
you need
this
to
sort
do.
of process that happens on compiler's front end. There is a name for
It's
this.
alias analysis, no?
Yeah, sure. Sure.
Because like yeah, if you are reasoning over mutable things, and the same mutable thing can have more than one name, then yeah, you have to deal with that, and that
Yeah.
may be.
Which we will, because we're gonna have aliases in the future in Karuta. So we're gonna suffer from that anyway. Uh, partial normal termination. Partial correctness reason does not say anything about whether or not a program terminates normally. It just says if a program terminates normally, then such and such is true. This makes reasoning simple, of course, but it's only part of the story. We have to also prove termination. There are three ways that a program can fail to terminate normally. Bottom, number one, infinite loop. This is a programmer error due to the calculation not being progressed towards its goal. There is, how should I say, there are strategies that you can leverage to try to identify some corner cases of that, such as if you have a recursive function that and you and you and there is an infinite loop there because you're missing a base case. For that particular infinite loop problem, you can add an integer that counts how many times the function was called. If that function, that counter hits a threshold, you stop the execution and inform the programmer instead of just let it consume the memory. But
Yeah,
that's
that's
again a very
the
corner case scenario. You cannot solve
that
a general because this would mean solving the halting problem.
that's the low level approach, and it's basically saying, yeah, okay, no, you have to have an upper bound, and if you see that your loop is hitting that upper bound, then that's an error because it's probably infinite unintentionally, right?
Yeah.
This is an idea straight from NASA, by the way. Um, but of
Really?
course, there's always the other. Yeah, it is like
Wait,
there's
which
the
idea? To have the counter?
yeah. There's a
Really?
paper
Okay.
about the power. I think it's called the power of 10 rules. It's basically an approach for because like NASA they have to send computers into space, right, in satellites and such, and probes and whatnot, right? You don't have access to those, which means the codes better be right before you send it, right?
No, definitely. I'm more in favor of sending the safest code to space. It's just because I guess I'm suffering from the problem of it's so dumb of an idea, but nobody thought of it, so it sounds like not a big deal, but nobody had it before, so it was a big deal eventually, at some point.
Yeah.
And right now it
Of
seems
course,
obvious.
yeah, and of course, there's always the other alternative, which is you go high level and say, yeah, no, I'm just gonna use a total language.
Sure. Yeah, sure.
Infinite
Um,
loops are literally illegal.
yeah, probably dependency type languages and stuff like that.
Yeah, because it turns out infinite loops are not something you want when you're doing proofs, right, of theorems.
Yeah. For us in particular, we have execution blocks because the data flow variable is not sufficiently bound inside an operation. This is a programmer error due to overlooking a calculation or deadlock situation. And exceptions. In this section, we consider only one kind of error, a type error, but similar reasoning can be done for other kinds of errors. More observations. So progress reasoning, each time there is a loop, there is the danger that will not terminate if you're not using dependency type languages. To show that a loop terminates, it suffices to show there is a function that is not negative. Yeah, this is also, again, a particular form of doing induction. Suspension reasoning, it suffices to show that all variables are sufficiently bound before they are used. Now that we have the non-determinism because of the message passing model, we do have primitives that allows us to check for that, so sure.
Uh, yeah, I have something to say about that, but we can wait until after this reading session.
For each use of the variable, tracing back all possible execution paths should always come across a binding. And finally, type checking, which happens before running the thing, checking the types are correct. Do you want to say something now or after 6, 7?
Let's just finish the the reading actually, because this is about Carta, it's not about the book.
Yeah, okay. Okay, so program design in the large. So these are essentially guidelines, um, a summary of the lessons that the authors have learned. I didn't notice that this is from Churchill. Okay. This guy is everywhere, isn't he?
Yeah, he
Um,
kinda is.
a bunch of lessons from the people that made the book, and I think some of them may be hot takes or not. Let's see. So, programming the largest programming by a team of people. Managing teams so they work together efficiently is difficult in any area. For programming, it's especially difficult since programs are generally quite unforgiving of small errors. Programs demand an exactness which is hard for human beings to satisfy. We call this software engineering. This section builds on section 3.9's introduction to programming in the small. We explain how to develop software in small teams. We do not explain how to do for larger teams. Um, and the reason is because programming on the large adds a lot of problems that are not programming related. They are more like the cost of having that many people, uh,
Coordination problems, essentially.
coordination problems, knowledge sharing problems. So that's more soft related in comparison to the hard skills that you have when you are working on a small team. So design methodology. Much of the existing literature consists of extrapolation based on limited experiments, such as rigorous validation is so difficult. To validate any new ideas, several otherwise identical teams would have to work in identical circumstances, which is very rare. So managing the team. Okay, so what the authors think about managing the team in the large. Compartmentalize the responsibility of each person. For example, each component can be assigned to one person who is responsible for it. We find a responsibility should respect components' boundaries and not overlap. Yeah, but this is for responsibilities. It is the opposite for knowledge. Everybody should be replaceable.
Yeah,
There should be no team member who is indispensable. The problem is that this is not this doesn't have short-term value. This only has long-term value. This means
which
there
means
is a
it's often
problem
neglected.
convincing people that care about the
Yeah,
short-term value that this matters.
yeah.
Uh, which is I redirect you to patterns of software last chapter. It talks about that. carefully document each component interface. Again, long-term value, not short-term value, which means hard time convincing others that this is worth it. Um, Develop methodology. So there are ways to organize software development. None of these techniques is really satisfactory, in combining them doesn't help much. The main problem is that they all rely on the system requirements and specification to be fairly complete to start with, which is usually not true.
Yeah.
So that's the main thing. The people that we build software for, if you ask them what they want, not even they know what they want. Which
Yeah.
means that there is a mutability problem happens on the specification level. And actually, I'm going to take this as a tangent because there is a conflict of interest in here. When you're, let's speak database, for example. This applies in all areas of software, but I particularly think this is problematic on database space. If you have a relational database, you have a DBMS, and you have a set of requirements and a specification on what the requirements are for the business. If you spend a lot of time on your database experts building such system, and you change your mind afterwards, that will cost you because relational database, they have a very rigid and crystallized way of building them because you have to check, you have to make constraints, you have to make checks, you have to make guarantees, you have to make all of that stuff to that fits perfectly that particular business. And depending on what mutates later, it's going to be more work to rearrange it because it's very well constrained. It's built to make something very precise, and the tooling that we have doesn't have the flexibility that we may want if we want to change our minds. And that gives the impression that the problem is the relational model then. Like this gives the false impression that we can't move as fast as we want because we chose a tool that obligates us to be slow. And that's a problem because that
Well,
means, go on.
well, yeah. In fact, the problem is not the database. The database is just showing the fact that you don't know what you're doing, basically.
I know, but people like to believe that you should be able to move fast even if you don't know what you're doing. And if you have a very talented and expert group of database developers that they can rearrange things fast, that's one thing. But if you have like people that are not that well versed in that particular SQL idiom that you guys chose, it may take a while to rearrange all the tables and the updatable views and the triggers and the cascading and the role level access and the schemas, all that stuff. Uh, that may give the impression to the person that is changing his mind that actually this is not a good thing because it doesn't allow me to change my mind. Um, and this is also links perfectly with the conflation between the idea and the tool because they because the tool sucks to implement such a thing, then they target the idea. Like, I don't want relational at all because relational means slow. Changes are slow. But that's because of how the tool implements the idea and not because of the idea. If we could just put a helmet on the top of the database guy and he just vomits the solution, then any change is okay. The problem is that you have to spend time materializing the thing. It doesn't serve to be on his head. So the tool, like there's a whole conflation between the tool and idea again, all of that stuff. So I think this is like a tangent, but I think it's worth it because I think this is a problem of the long term versus how how often you want to change your mind and what is the cost you're willing to accept to be able to change your mind.
Yeah.
Okay, so develop methodology. Start with a small set of requirements, which is a subset of the complete set, and with a complete system that satisfies them. The system specification architecture are empty shells. They are just complete enough so that a running program can be built, but do not serve the user problems. This is already controversial because maybe the smallest set of requirements that work for that particular program will be expensive to change later, which means that being an MVP may be not enough. It may be not enough
Mm.
because maybe the fastest and the smallest set of requirements will be tough to change in the future. So for example, let's suppose for a moment that original Karuta didn't have a store module and we were actually using direct finger tree function calls in the code. And in the future, we decide to actually we're going to drop finger trees. That means that we're going to have a lot more work because everything is going to break. So it's going to be expensive in the future if we change our minds. And it is because of that potential future that we decided that, okay, we're going to actually have a module that exposes an API, and if in the future we change our minds, we can just change that module and everything else works. In that case, we could foresee the cost, and we made changes accordingly. But that is not always true, that you can foresee that. That comes with experience, try and error, reading, all of that stuff, so you can learn from previous mistakes and say, this is going to bite our butt in the future. Let's not do the MVP like that. So that's what I have to
Yeah.
talk about the small set of requirements. Go on, Marie.
There's also the fact that, yeah, if you take the care to do that, people may think it's too expensive in the short term, right? Even though
Yeah,
it's less expensive in the long run.
yeah. Yeah, but usually their answer is there may be not a long run. We may die before that. It's again, last chapter of patterns of software all over again.
Yeah, that's basically Keynes, basically.
That's also true. Uh, then continuously extend the requirements, extend the older layers as needed to satisfy them. Using an organic metaphor, we see that the application is grown or evolved. Yeah, they removed this in the new version. They don't have the evolved here. This is sometimes called an evolutionary approach, but there is a caveat, which in this version is not here. There is a footnote explaining that this is the wrong nomenclature. But we don't need to go over that. At all times, there is a running system that satisfies its specification and can be evaluated by its potential users. Do not optimize it in this stage. Just make it work. Do not worry about the overhead of these abstractions. Performance optimization can be done near the end of development. There is a caveat to this, which is if it's not costly to do the optimization right now, such as like you already know the code that will be there, it's just changing 2 lines, then or changing a particular function, fine.
Or
Like
choosing the right data structure, because nobody wants linear
not no 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 no
time
no no no.
spent
Not
in a
only
loop.
choosing the correct data structure, if the correct data structures provides enough functionality. You may have a data structure implemented, but it doesn't provide enough APIs. So good for you, you have the thing, but you don't have a way to interact in the way that I wanted. So, too bad. It was not the case with finger trees. We do had everything we wanted. So in that case,
Lemos,
it
the
worked
whole point
perfectly.
of a finger tree is that it's a general purpose finite sequence.
I know, but if we have a general purpose find a sequence that doesn't provide, I don't know, um, head or tail alternatives, I don't care.
If if it didn't have head or tail, it wouldn't be general purpose.
No, it would still be general purpose, but in progress implementation. Maybe it's not even released officially. Maybe. Like it's one
Ah, but
thing.
then
Yeah, I'm just saying
you're
that
talking
this
of,
may be true, and you need to
you're
take
talking about
that
a
to account.
you're talking about using a half implemented data structure. That's not the same data structure as a fully implemented version.
Yes, I'm talking about For example, in Racket, right? We wanted the implementation of a B plus tree. We could have found a half-baked version of it, and then we have the option of finishing it for the library's author or using the C version. But in that case, we didn't have the option because there was no half-baked B plus tree in Racket. We had to go with the C version. But that may be the case that there is something in progress and the authors are still developing something, but you need to make a decision now. You cannot wait for them. That may be
That's
rare,
fair.
fair enough, but I need to say that. Reorganize the design as necessary. During development, to keep a good component organization, components should encapsulate design decisions to implement common abstractions. These are reorganizations sometimes called refactoring. There is a spectrum between the extremes of completely planning a design and completely relying on refactoring. The best approach is somewhere in the middle. I think I disagree. I don't think it's the best approach is the middle. The best approach is doing both. Uh, but then
If you do
I
both,
would
isn't that in the middle? Because you'll be doing a planning for some parts and doing refactoring on other parts.
no. I'm proposing you have a plan for the full thing, but the plan you don't have 100% confidence on the plan, but you do have a plan. So rewrite in OCaml the parser and the preprocessor. Then we have a runtime thing written in Erlang that allows us to have some important behavior for logic programming. And in the OCaml version, we write the symbolic bytecode representation, assuming the existence of the runtime library. And then when calling the database thing, we're just gonna utilize the fact that it's gonna be written in Erlang anyway. We have a full plan of that. We had a full plan, top to bottom. However, our confidence level was not 100%, such that we changed. Okay, we're not going to write symbolic representation anymore. We're going to write Erlang's EST instead. Let's assume for a moment that we already have written code that generates symbolic representation. After such a decision, we would refactor it. So, what I'm proposing is you have at least a vague idea of top to bottom, and the portions that are a little bit blurry, those are the ones that will probably suffer refactoring.
How
But
is
at least
that
you have a
not in the
sketch.
middle? How is that not in the middle, Lemus?
Well, because I'm proposing to you to do both. I'm not proposing you to do halfway this, halfway there. I'm proposing both.
Well, the best approach is somewhere in the middle, not necessarily the exact middle. The point is, you have a sketch of a plan, and you may have some details that you need to fill in later, right?
Yeah. Yeah, but you are like you're still designing top to bottom. You're not like because the way that this is written, I would assume that the authors would be okay if you plan just the beginning. You don't know the end. And
That's
you don't know the middle.
that's not that's not really um, that's not really how a partial plan looks like, Lemus.
Well, I heard that partial plans in my life that work like that. We know the beginning and the middle, and we don't know the end. Or we know the beginning and the end, and we don't know the middle. In our case with Karuta, we know everything. We just are not written in stone about it. And it's
Mm,
usually how I do work, like in the real world, like closure work. I usually think of something top to bottom in my head at start. Like I 100% know that at least a sketch of everything I have in my head. And some places I'm not that confident it will turn out to be that way. And those are the portions that I'm willing to do some refactoring on it. But at least a first idea of top to bottom I try to have. If I don't have, I start to get anxious because being capable of having a sketch of top to bottom in my head means that it may not be feasible, either because of a skill issue on my part or because of a technical problem. which both I need to do something about it on both cases. But I usually try
I
to have a
see.
full plan. I don't like this idea of having halfway plan.
I don't think that's not the meaning I get from this at all, Lemus. Like there's a difference between saying, okay, I planned half of the approach versus I have an idea of how to do this thing completely, but I don't know the details. I think the authors are suggesting more of the latter, where okay, um,
Okay,
I
I
have
see.
some idea of how to do this thing, but I'll figure out some of the details as I go. You see?
Okay, that's fair enough. Yeah, it's up to interpretation here. I'm just specifying exactly the possibilities here. Uh, the thing to thick approach, which is what the authors are calling this, has many advantages. Bugs of all sizes are detected early and can be fixed quickly. Deadline pressure is much relieved since there is always a working application. Developers are more motivated because they have quick feedback. Users are more likely to get what they really need because there's already something in production. The architecture is more likely to be good since it can be corrected early on. All of these have caveats, but especially this one, that's not necessarily true because there may be
Well,
some architecture choices that will be expensive to change afterwards.
I'm not saying that the architecture will be good, only that it's more likely to be good,
Yeah,
right?
no, but I think there should be like a more um, less optimistic take on this statement. The user interface is likely to be good since it's continually improved during the development process. Yeah, this is front end, and I don't know much about it. For most systems, even as very small ones, we find it is almost impossible to determine in advance what the real requirements are, what a good architecture is to implement them, and what the user interface should be. The thin to thick approach works well partially because it makes very few assumptions upfront. For a very complementary view, recommend studying extreme programming, which is another approach that emphasizes the trade-off between planning and manufacturing. Hierarchical system structure. So this is talking about this image essentially. So how should the
Yeah.
system be structured to support teamwork and thin to thick development? And we're going to talk about the hierarchical graph approach. The application consists of a set of nodes where each node interacts with some other nodes. Each node is a component instance. Each node is itself some small application and can be itself be decomposed into a graph. The decomposition bottoms out when we reach primitive components that are provided by the underlying system. In our case, the
Yeah.
kernel language.
One point in that paragraph that we should emphasize: the components will need to have well-defined interfaces, right? That's the whole point.
Yeah.
Uh,
So this is what what we did, for example, in Karuta for the store module. We defined a well-defined interface, and then we figure out the internal implementation details later. Uh, but this is a very good approach, um, which is kind of funny coming from a book that uses a dynamic language. Because one of the marketing points of dynamic language is that you should be able to change the interface easily. So it's kind of funny that the book itself, although it is a dynamic language, it is actually proposing something that you would expect as static language guidelines, which is do whatever you want in an implementation. I don't care, but you need to have well-defined and usually strongly also advertised simple interfaces, and the mass can be under the implementation level. You don't expose a complex interface.
well, these guys have a background in Prolog and probably Lisp as well, right? So kind of to be expected because this whole idea of okay, the interface is a mess and I don't care. It's more of a JavaScript slash Python thing, right?
Well, that would be the more modern versions, right? The worse is better thing. It was the bad interface would be C, right? Uh,
Bad interface would be C.
yeah, isn't it
Um,
the New Jersey versus MIT thing, Lisp versus C?
well,
Pretty
yes,
much. That's what
but
I
also
remember
there's
at
nothing
least.
inherent. Well, there's nothing inherent to the C languages that pushes you to have bad
No.
interfaces,
But
other
it's
than the
about the
fact that you have to
culture.
use.
It's about the culture, not about the tools necessarily. The
Well,
tools
no, culturally,
may
yes, totally.
incentivize by their technicalities. That's true. But you can avoid these mistakes in C. We all seen this before, right?
Mm. Actually, I should probably make a small retraction. This is more of a JavaScript, not Python thing. Python, at least, they have it going for them that, yeah, this needs to look nice, which means you need to have a nice interface, right?
Yeah. Yeah. And then it goes to static versus dynamic structure. This consists of a component graph that is known when the application is designed. These components can be linked as soon as the application starts up. Each component instance corresponds roughly to a bundle of functionality that is sometimes known as a library or a package. For efficiency, we'd like each component instance to exist at most once in the system. If a library is needed by different parts of the application, then we want the instance to share the same library. For instance, a component may implement a graphics package. The whole application can get by with just one instance. And the dynamic structure is the opposite. So you may want to link to new components at runtime. You may want more than one at runtime. Several instances of a component are needed. If you have a database interface, for example, I don't know which program would do that, but you may, whatever.
I think a more, uh, I think a clear example would have been an HTTP server where you need to handle like each request separately, right? So you may have a separate process or thread handling each request.
Sure, but if you're using transactions, why do you need more than one database interface? Just share the
Uh,
same one among the threads.
well, maybe you're collecting data among external databases. Maybe you don't own the database yourself.
Ah, okay, that's fair enough. Depending on whether there are one or more external databases, yeah, that's the example. One or more instances of the component should be loaded. And then, yeah, I don't know about you, but when I was reading this, I was more like, this is talking about linking, right? It managed to talk about it without mentioning it once,
Yeah.
which is
Well,
impressive.
it's not just about linking. That certainly fits, but it's also about like the whole idea. Actually, this is more of a Zig thing of um, trying to do push as much of your design to the static side as possible, right? Trying
Yeah.
to allocate all memory when you initialize the program and all that. That
No
plays
mallocs
into this
for us.
trade-off. Yeah, that plays into this trade-off as well.
That's fair enough, but yeah, but it's still focusing on libraries. Like it's not keeping it generic. It's giving examples. So that's why for me, okay, you are definitely talking about linking, and then it immediately goes, okay, here's an example, linking. Like, so we have functors and their instances modules and their compilation units, which well, we're also gonna try to do something like that for Karuta. It's probably not gonna be as elegant because it's us, but that's essentially how that works. And you can have a dynamic structure, which is essentially instantiating the functor at runtime. So like a procedure, the functor may have external references. Instantiating a functor gives a module, which is a set of language entities created by initializing the functor. So that's how it would look like. Then we have component communication, which I think it's a very nice separation here. So we have procedure. So this is the most basic type of communication between components. It's sequential. The caller is not necessarily the only initiator. There can be nested calls when the locus of control passes back and forth. We have coroutines, which you also see in this book before, but this is also very common in programming languages as a whole, which is also sequential, but they keep interleaving. Then we have concurrency with synchronous, which are basically threads. Then we have concurrency
Yep.
with asynchronous, which is uh,
Message passing,
message
basically.
passing in this language done by the data flow variables or streams. Then we have the mailbox, which is Erlang. And then we have a coordination model, which I was kind of trying to think about. Components can communicate without the senders and receivers knowing each other's identities. Did we do this by accident in Mahjong? Like,
Mahjong.
yeah, like from the client's perspective, the
Kinda, but not really. I mean, it is what we did is more of a pub sub style thing. It's related to, but not quite the same thing as a tuple space. So yeah, we kind of did actually.
Yeah, because we have the decider, and nobody know, like the client doesn't know that he is talking to the decider, but he is. So like there is an abstraction, which in our case is the backend is working as the abstraction. The components are concurrent and interact solely through the common tuple space. One component can insert a message asynchronous, and another can retrieve the message. So this is the SSE. So like there's a whole message passing working within the thing, but you only talk to like the gatekeeper or something like that.
Basically, yeah, basically. Like there's actually a language called Syndicate which explores this idea as well.
Hmm.
But yeah, basically there's a shared context. You send messages to the context and they get passed to everybody else in the same context for you.
Okay.
So you don't know who exactly you're talking to, you just know that you are in a particular context, basically.
Yeah. So okay, so model independence principle. Each component of a system is written in a particular computational model. Um, so they may change the component may change drastically. Stateless component can become stateful or distributed, vice versa. We need to keep the interface because that's what matters. Uh, this is an important modularity property of the computational models. As long as the interface is the same, this property guarantees that it's not necessary to change anything else in the rest of the system. The interface of a component should be independent of the computational model used to implement the component. The interface should depend only on the externally visible functionality of the component. I would say even further, the interface in its most ideal form should give you a hint, well, should give you the impression the component is declarative. Like ideally, that may not be possible in all cases, which is understandable, but you should try your best to do that. And he proceeds to give a good example of that. So I would say interface matters most. Try to keep it as seem as declarative as possible. And then there's the example of the memorization that will happen using the lexical scoping trick anyway. And so the callers will not have the notion at all by the interface that is actually memorized. We've seen
Yeah,
this
they
before.
don't
I'm
need
not
to
gonna read that.
know that there's a mutable table inside of the procedure that caches results.
Yeah,
Like, the caller doesn't need to care about it.
yeah. A component is a compilation unit. Like to compile a component as quickly and efficiently as possible. Oh, this is talking about the holistic versus specialized thingy. So yeah, so this is essentially the TLDR is there are conflicting interests in here. If you want to optimize the shit out of the program, you have to explore the interactions between components, and that may not be possible because you want to keep the components as individualized as possible, and you may have third parties, which means that you don't have the luxury of inspecting something that you're going to be compiling with.
Yeah.
So these conflict interests, the the solution probably be something in the middle. There is a strong tension between these two desires. If the compilation is truly separate, then analysis cannot cross component boundaries. To do a truly global analysis, the compiler must in general be able to look at the whole program at once, which may also be a problem. This may be terabytes of data, of programming.
What
This
kind of program has terabytes of source code though?
um, it's a very good question. Very good question.
Actually, it may not need to be terabytes of source code, right? If you have a
Okay, let's put gigabytes and let's say it's a microcontroller. Done.
okay.
This
Well,
means
actually,
that
gigabytes is fair, like because a fun fact: the original C++ compiler for Zig before it went self-hosted, you actually needed to have like 16 gigabytes of memory just for the compiler to compile itself. Well, not for the compiler to compile itself, for the bootstrapping, right?
I
Because you need to
wonder
compile
I
it with
wonder
G++.
how much Jai requires because Jai is also written in C++. So there's that.
Well, Follow-up fun fact: after Zig switched to the self-hosted version, it now takes only 4 gigabytes to compile itself in the bootstrap mode.
Of course. Um, this means that for many statically typed languages, compiling large programs requires much time and memory. There are many clever techniques to try to get the best of both worlds, but this is still an active research topic, so like it is what it is. Commercial quality systems span the whole spectrum from completely separate compilation to sophisticated global analysis. Practical application development can be done at any point of the spectrum. OS doesn't do that because since it's dynamically typed, components can be compiled without knowing anything about each other, because this will only blow up at runtime anyway. This means that compilation is completely scalable. Compiling a component takes the same time, independent of whether it is used in a million-line program or in a thousand-line program. On the other hand, there are disadvantages. Less optimization is possible, and type mismatches can only be detected at runtime. Whether or not these issues are critical depends on the application and experience of the developer. Maintainability. So now we're going to introduce the notion of maintenance. So the process of keeping a system working well after it is deployed is called maintenance. And this is also a very like a criticism that I have for this book. I think that the process of keeping a system working well after it is deployed is called like there are two facets for this process of keeping a system working well after deploy, which is um, reproducibility. So like Nix and Geeks, and if you want to throw it in there, Docker as well. They serve to try to keep, because maybe the software is okay, but the environment that is surrounding the software changed so much that it doesn't even compile. I was watching Jonathan Blow interview during the gym, and the example that he gave, let's say third world war started and the internet is broken, so every package manager project is now fucked. And I was like, that is a good argument to not to try to actually download the dependencies locally to your machine instead of just relying on the uniqueness factor of an URL with a hash inside of it. That is a good reason, and I think this book doesn't mention any of that so far. So I think that's a criticism. You should mention that keeping
Uh,
system still working not only deals with programming, but also keeping the environment working. So
to be fair, this book is from 2001, no?
2001, 2003, but even then, like this is a problem since always, no? Like since the old back days, like oh, this program is using a C++ whatever standard, and and I don't have this compiler, this version of the compiler. Like
Oh, yeah, that is a problem sometimes.
the best way to social system. Maybe at the time that they wrote this, it was not yet realized how much of an issue this is. So maybe like this is anachronic in a way that now we know that this is a big thing, and at the time they thought it would not be a big thing. Especially because maybe back in the days you would just download the dependencies and put it in your repo anyway. You will not have all of these package managers and build systems and JSON and YAML and Toma and all those things. Maybe at the time they were just like, no, dude, just download the dot A of the thing. Fuck it.
Or download the source code and compile it yourself. That's also an option.
Yes, that's also an option. Yeah, but you may not do that because maybe the project is like a couple thousand lines. Uh, but yeah, that is definitely an option. From our experience here, from the important principles, we need to speed this up a little bit. So component design. There are good ways and bad ways to design components. A bad way is to make a flow chart and carve it up into pieces where each piece is a component. Much better is to think of a component as an abstraction. For example, assume that we are writing a program that uses lists, then it's almost always a good idea to gather all list operations into a component, which defines the list abstraction. With this design, lists can be implemented, debugged, changed, and extended without touching the rest of the program. This is very natural, but the fact that they are telling us this means that to some people, they actually like scattered the lists functions implementations.
I
Uh,
mean,
for example, so we want to use the program with lists that are too big for main memory. It's enough to change the list component to store them on files instead of in main memory. Encapsulate design decisions. We can say the component should encapsulate design decision. That way, when the design decision is changed, only the component has to be changed. Yeah, very similar to the previous point. This is a very powerful form of modularity. The usefulness of a component can be evaluated by seeing what changes it accommodates. For example, how you're going to do characters.
yeah.
Avoid changing component interfaces. This is essentially repeating what we said before that, well, if you need the interface to expose something about Unicode versus ASCII, then everybody's fucked, and we're gonna have to do some breaking changes. Try to keep that as like internal as possible, keeping the interface. Again, same thing as before. Yeah, this is also hot takes, right? Because fewest possible external dependencies, which means no npm library to do plus, right?
No left. If you want left pad, write it yourself. It's 2 lines.
Yeah, don't do that. Man, imagine for a moment that okay, that what Jonathan said actually happens. Like we can't run our website because it only uses npm libraries, and we have like 80 of them. And now that we have no internet, nobody can run the thing. Like,
Yeah, yeah.
okay, then does a full example of latex, which it's essentially saying you should download your shit. Like if you're using something from working as a treating as a library, external library, you should have a copied version of that. To add maintenance, it's much preferred to have copies of the style files in each document directory because it keeps the environment sandboxed in a way that the document can still be compiled. Again, this is the same thing I was talking about. These should have like a revision 2020, I don't know, 2015 already, I don't know, where all of these portions of the code that are mentioning this, they should like nix geeks, footnotes of the way. Fewest possible levels of indirection. So this is talking about dangling pointers, which is, well, less of a problem for us because we tend to use high-level languages that have like better abstractions to solve this type of thing. But this can still happen, right? So when A points to B, when updating B requires updating A. Well, today we don't have to do that because if B updates, because the way that most package managers do their work, we don't need to update A necessarily because we have a saved version of the previous version of B, so it's fine. But in the old days, where you're copying source code, sure, so you need to update A with the new probably interface changes of B. In this case, there is a dangly pointer, and action at B may cause A's pointer to become dangling. B doesn't know about A's pointer and so cannot prevent such a thing
Well,
because B is a
this is more
library.
yeah yeah this is more conceptual actually. Like it's talking in terms of pointers, but it applies to libraries. It applies to or it applies to abstractions. It applies
Yep,
to
yep, yep.
dependencies. It applies to actual objects in memory as well, right?
Yes, and then it talks about the examples of problematic pointers of symbolic links in a Unix file system and URLs. URLs are known to be extremely flaky, which are often referenced in printed documents, but their lifetime is usually much less than of the document. This is less of an issue, but the interviewer made a point of like, what happens if GitHub goes down? Yeah, then this restarts to become very true. So you should rely on something else. Dependencies should be predictable. Consider a localized command that is guaranteed to retrieve a file over a network and make a local copy. It has a simple and predictable behavior, unlike the page caching done by a browser. Um, Page caching is a misnomer because a true cache maintains coherence between just smaller details. Making decisions at the right level. Yeah, this is talking about making a functionality mandatory at specific levels of the abstraction layers. So If you have a timeout, there is a revocable decision made at a low level. That means that everybody on top of it will break. So that may not be the correct level to introduce that requirement. Documented violations. Whenever one of the previous principles is violated, you should document it. Nobody does that. We are actually lucky if people even
That's
make a comment about it. Imagine a document.
yeah.
Simple bundling hierarchy. Yeah, this is funny because I read this and I was like, okay, these guys are fans of Fortran. Nice. Um, so this is a hierarchy guideline for like division of your program components. So if possible, put the whole application in one file. The file may be structured in sections corresponding to components. Yeah, don't do that. Actually, I disagree fundamentally. Don't do that. If the
Why?
above is not because aside from very particular, usually small programs such as a script, this doesn't. This is terrible because
Why?
this mean because this means that you are relying that the separation of sections is going to be done by the programmer, and I don't trust the programmer a tiny bit, so I would rather have different files at least.
What happens if you're using ML?
If you're using ML, well, we have a little bit of a convenience because you can make the sections as modules, which facilitates a tiny bit. But you don't have to. You don't have to use modules. Maybe the programmer is a bad programmer, and he does an OCaml program that has just a bunch of dangling functions everywhere. So not even that
What
saves
happens
you.
if what happens if it's SML? In SML, files are not modules.
Well, the same principle applies, right? You can just have a bunch of dangling functions.
Yes, but separating them into files doesn't help then.
Oh, it does. Because at least in my head,
It
the
doesn't because it actually just breaks up your scope into multiple places, right? Your global scope, I should say.
well, I'm never working on the global scope. If you're doing SML or ML, you're reading on the level of functions.
But the functions are defined in some scope, right?
No, yes, the functions are defined in some scope, but at least having the separation of files, aside from files
But that's
having like nonsensical names, at
no,
least
but that's
that gives you
kind
something.
no, but that's kind of the point. If you are using SML, not OCaml, that means that files are not modules, right?
Yeah, but the
That means
files will
that
have
if you're
names.
not no, yes, they will have names, but if the files are not modules, and you define a function straight into the file, not inside a module, that function is in the global scope, no?
No, but I'm not talking. My problem is not necessarily about the scoping. I'm not talking about scoping issues in here. I'm talking about there is a portion of here where I yeah this section. I don't have a bunch of cache in my brain. Having more files facilitates my mind to not have to cache that. If I have a big file, I usually start to think that all the file matters for the understanding of everything because they are in a single file.
Why?
In the
That
SML world that would be a choice because in the Fortran world that's a technical problem. For SML it's on purpose. So that would be I would imagine that there would be a reason for that. So like I don't like this idea of having big files. I don't like that. It may be a personal preference because for example you can just say tag the entire file, treat it as you're going like when I say tag it, like use the lookup thing that Emacs provides so you can jump through the definitions, and then just ignore that it's a single file. Sure. But I got this from Breno from back at my F sharp days. I don't like big files.
hmm.
If the above is not possible, for example, there are files of different types or different people are to work on different parts simultaneously, then put the whole application in one directory If the above is impossible, put the application directory hierarchy with one root. Sure. Okay, future developments. Man, this is going to be a huge recording. Components and future of programming. What matters for us to talk about in here? I don't think that matters that much.
Ah, JavaScript, web. There we go. That's the top.
Yeah, for components to make programming accessible to application users, not just professional developers. But it does change the lives of professional developers. As more and more useful components are developed, the generality of programming will increase. The basic elements used by programmers will more often be large components instead of fine-grained language operations. And then there's the example of Visual Basic. The main bottleneck limiting this
Java
evolution is the
beans.
specification of component behavior. Yeah, vague specifications to make components simpler, better factorize the functionalities, and improve how they can be connected together. Yeah, compositional versus non-compositional design. I think this is the last thing. Yeah. So this is essentially doing a comparison between how the authors and I'm gonna put myself on that. How we view how design should be done, which is compositional, and how nature does it. So uh, a component graph is one in which each component is a node, and there is an edge between components if they know each other. In a composition system, the graph is hierarchical, which means that each component is only linked to its siblings, children, and parents. As a result, the system can be decomposed in many ways into independent parts, such as the interface between the parts is small. And in a non-compositional system, the component graph doesn't have this structure. It tends to be bushy and non-local. Bushy means that each component is connected to many others. So like it's a very holistic, almost like a complex system in a way, in the sense that the fly of the butterfly there changes that,
And it
which is
changes
like
everything.
kilometers away.
Yeah, the
uh,
butterfly is the Fire Nation now.
yeah. So non-local means that each component is connected to widely different parts of the graph. Decomposing the system into parts is more arbitrary. The interface between the parts tend to be larger. This makes it hard to understand the components without taking into account their relation with the rest of the system. One example of a non-compositional graph is a small word graph, which has a property that the graph's diameter is small. And then we're going to have a very common sense explanation why the hierarchical composition is better for humans. The main constraint for humans is the limited size of the human short-term memory. A human being can only keep a small number of concepts in his or her mind simultaneously. This varies, but and this is especially not true with very smart people. Smart people can actually keep a gigantic amount of number of concepts in their heads, but the
Or
problem is that
they
they are
just know.
scarce. We don't have a lot of
Actually,
smart people.
actually, they just know how to fold things into a small number of concepts more efficiently.
I don't buy that at
Like they're
all.
good at
I
they're
think
good at
people like
compression limits.
Zozing and Jonathan Blow and probably all the author of Zig and all those people, they actually can keep a very large number of concepts in their head. Partially because they are more intimate with those concepts, so that they are familiarized with them, so that it's not that unnatural for them to hold them in their heads, and partially because they are smarter, like they can actually hold more information in their head. But Marinho may be right. Maybe they just have a recipe, a secret recipe, in which they can factorize everything to small parts more efficiently than everybody else. But I strongly don't buy that. I think they actually can keep more stuff.
Let's disagree on this.
A large design must therefore be chopped into parts that is each small enough to be kept in single individual's mind. Without external aid, this leads humans to build compositional systems. On the other hand, design by nature has no such limitation. It works with the principle of natural selection. New systems are built by combining and modifying existing systems. Each system is judged as a whole by how it performs in a natural environment. The most successful systems are those with the most offspring. Therefore, natural systems tend to be non-compositional. It seems that each approach is a kind of extreme. Human design is goal-oriented and reductionistic. Natural design is exploratory and holistic. Is it a meaningful question to try to get the best of both worlds? We can imagine building tools to let beings use a more natural approach to system design, Yeah, so there is a ze casting.
Oh, that thing. I see.
Yeah, so this is a note-taking strategy that kind of assumes that knowledge works in a more holistic way. It's very fascinating the fact how this was done by the back in the day of having like um,
Actual
a
paper notes.
suitcase that you um, go around with, and when you want to make a note about the universe, you just open that, and there's like piles and piles of notes, and you have to like there's a protocol specifying how this new note connects to the already existing ones, and yeah, it's written in here. So there's that. So like it's you and I think um who else said it uses this? There is somebody in the server that uses this that I don't recall. I actually buy the idea that knowledge is a holistic thing. I just don't have the patience and the organization discipline necessary to do this type of thing. Um, in this book, we also consider this direction further. We focus on the compositional approach. Further reading. Yeah, so this is the Mythical Man Month. This is a very famous book. I haven't read it. Software Fundamentals is very famous, and the Cathedral and the Bazaar. I already read that. Recommend that.
That's really good.
Beyond object-oriented programming. So this is talking more like a recommendation from Clement. Well, this is actually a bunch of recommendations for us to read as next book club. So actually, let's skip all of that, and then finally we're done with that. Okay. So we're gonna finish chapter 6 next session, right? That was the agreement.
That's the
So
plan,
it's
yes.
6.8 and
That's the plan.
6.9. I'm gonna finish the recording now.